Hello everyone. Welcome. Do the fun problem of the day displayed on the screen here while we wait for more people to come in. Okay, I'll start explaining this problem now. So the shaded area equals the entire area minus that of the white area. So now the white area can be represented as 4 squares and 4 of these triangles. So each square has area 1, and each triangle has base 3 and height 3, so it has area 4.5. So the area of the shaded pinwheel is 25 minus 4 times 1 plus 4.5, which is 6. Okay, so I'll be starting to go over the homework now. So all of you did well on the homework of those who submitted. And now I'm just gonna go over the two most commonly missed problems. Okay, so for ABC, A, B, C, AB is 15, BC is 39. So by the Pythagorean theorem, AC equals 36. Now let AD be X. Then BD equals square root of X squared plus 225. And it also equals CD plus 9, which is 36 minus X plus 9, which is just 45 minus X. So now you can square both sides of this, which tells you that X squared plus 225 equals X squared minus 90X plus 2025. So 90X equals 2025 minus 225, which implies that X equals 20. And since we defined X to be the length of AD, we have that AD is 20. Now, here's another problem that many people missed. So the largest square that's possible would look like this. Okay, so the area of the square can be broken up into 5 pieces. The largest piece is the area of this inner square, and the other 4 are these are the 4 triangles here. The 4 triangles outlined in red here. Okay, so the area of this inner square is 3 squared, and the area of each outer triangle has a base of 3 and a height of 1. So the 4 of them combined have an area of 6. So the largest area is 3 squared plus 6 equals 15. Okay, so Euclid. He's considered the founder of geometry. He first represent he Euclid first wrote a book about geometry called Euclid's Elements, and it covered a lot of geometry. So now this is going to be an overview of what we're covering in class today: area, analytic geometry, and 3D geometry. So first of all, the area of triangles. The area of a triangle is just the base times the height over 2. Okay, now Heron's formula. So Heron's formula says this, where S is A plus B plus C over 2, and S is commonly referred to as the semi-perimeter of triangle ABC. So- And none of these terms will ever be negative because of the triangle inequality. This is who Hero of Alexandria was, and the area of a triangle in which every side is length 5. You could do this with just by noting that it's an equilateral triangle, but if you use Heron's, this is what you get. Okay, now here's your first example. Yes, uh, I'm aware that we discussed this triangle last class, but this time I'm asking you to use Heron's just as an exercise. Okay, so the semi-perimeter of this triangle is 13 plus 14 plus 15 over 2, which is 21. So the area is 21 times 21 minus 13 times 21 minus 14 times 21 minus 15 equals square root of 21 times 8 times 7 times 6, which is 84. Okay, now for circles. These are for triangles. So an incircle is the circle that is tangent to all four sides of the triangle. And the in center of it is the inward circle, is the in center India. Now the circumcircle is a circle that goes through the 3 points that are the triangle's vertices. And its center is just called the circumcenter. Now, here's a theorem about the area within incircle. So it says that A equals RS. And you can prove it pretty easily. The area of this piece, okay, the area of this piece is A times R over 2. This piece is C times R over 2. And this piece is B times R over 2. And so when you add these up, you get A plus B plus C over 2 times R, which is RS. And now here's our next example. For this problem, a hint is that the ratio of areas when both triangles have the same height is just the ratio of their bases. Okay, so I'll start explaining this. So the ratio of AE to EC is, so the ratio of the area of AED and BEC is, so these are similar, and then you know that these are in a 5:3 ratio, which gives you this. And then you have that ABE over BC equals AE over EC, which we already know to be 3/5. And you can do the same thing for ABE over DEA, so A equals 3/5. And now this can tell you, this can calculate out the area of ABE and DEC. And so you get that the area is 9 plus 25 plus 15 times 2, which is 64. And here's another example. Okay, so for this problem, so they overlap to form a square. One side length is 15. So the squares have both have side length 15, which means that the squares look like this. But the 15 doesn't tell you the overlap here. So 25. This is 15 and this is 15, but you're also given that this is 25, so this gap overlap is 5. So the part of the rectangle in both squares has area 5 times 15, and the entire rectangle has area 25 times 15, and you can cancel out the 15s, and you can cancel out a 5, which gives you 1/5. The problem wants that as a percentage, so it's 20%. Okay, okay. Circle areas. The area of a circle is pi r squared. And here are definitions of a circle. This is a sector. This is a segment. This is a chord. Yeah. And here are the probably the two most common types of sectors. Semicircles, which are just half a circle, and a quadrant, which is a fourth of a circle. Okay, so areas of sectors. It's just for a sector of that covers an angle of theta. In degrees, it's theta over 360 times pi r squared. So the area of a segment. Um, this is probably more advanced than AMC8 for the general case. So basically, it's the area of this sector minus the area of this triangle. And the area of this triangle is, it can be found in a couple of different ways, but I don't think there's any way that doesn't involve non-AMC8 level stuff. Okay, here's your next example. Alright. And for this problem, express your answer in the form a- in the chat when you send. Please send it in this form, where a and b are integers. Okay. So the area of this small thing has area 4 pi. This has area 16 pi, 8 pi. This 18 pi, and this 32 pi. And so when you add these up, you get 60 pi, which equals pi r squared, which tells you that r equals square root of 60 equals 2 square root of 15. Okay, here's your next example. Okay, so the radius is 20. So this is 20. So this quarter circle has area 20 squared pi over 4 equals 50 pi. And this triangle has area 20 times 20 over 2 equals 200. Sorry, these are supposed to be 10. Okay. So each of these, half of a curve, is 25 pi minus 50. So the area of this is 50 pi, 50 pi minus 100. So the area of the white regions is simply 50 pi minus 50 pi minus 100, because that's the area of this minus the foot minus the strange curve, which is 100. So all, to calculate this, the sum of the shaded areas, can't see that, the sum of the black, sum of these shaded areas, you just subtract 200 from the total area, which is 20 squared over pi over 4, which is 100 pi minus 200. And here's your next example. Okay, so first we consider this, which is given to have an area of 8 pi. So then pi r squared over 2 equals 8 pi, which means that the diameter or the length of AB is 8. So you're also given that this arc has length 8.5 pi, and that tells you that pi RB equals 8.5 pi. So the diameter, which is length AC, has length 17. And now you apply the Pythagorean theorem to BC, and that gives you 15. So the radius is 15 over 2 equals 7.5. And here's your next example. Okay, so the area of the square, we first need to calculate the length of its side. So the side length is made up of two congruent radii, which is 2 times 3, which is 6. Sorry. And then the area is 6 squared equals 36. And now you're subtracting out the area of 4 quarter circles, which equals the area of 1 full circle. So the area is 36 minus 4 times pi 3 squared over 4, which is 36 minus 9 pi. And 36 minus 9 pi is less than 36 minus 9 times 3 equals 9. So the answer is clearly A. Okay, so analytic geometry. It's also known as coordinate geometry or Cartesian geometry. And so it's the study of geometry using a coordinate system. And here's what a Cartesian plane looks like. The origin usually is used to represent 0, 0. So the first way to write the equation of a line is point slope form. In it, you get that y minus y1 equals m times x minus x1. It's where you're given the slope of the line and unknown points, and xy can be used to describe the line. This is a generalized form of point slope intercepts form, which is y equals mx plus b, where m is the slope and b is the y is the point on the y-axis in which the line touches it. So the slope is defined as the change in y over the change in x. And here's how you derive slope in point slope form. Now, here's your first problem. Okay, so first, please don't put messages in the public chats unless you really want, unless you have a question. And please don't put answers to questions that are still up on the board, please. So this uses the distance formula. It has a fancy name, but it's really just the Pythagorean theorem. It's basically the area between 2 points, x1, y1, x2, y2 is x1 minus x2 squared plus y1 minus y2 squared equals, and in this case it equals 5 minus 2 squared plus negative 3 minus 1 squared equals root 25, which is just 5. And now here's your next example. Okay. For this problem, you'll need the fact that if m1 and m2 are the slopes of two perpendicular lines, their product has to be -1. Oh my god. Okay. So here's the slope of the radius, which is just 3/2. And since mr times m equals -1, m equals -1 over mr equals -1 over 3/2, which is -2/3. Okay, now on to translation. So, translations, transformations. There's rotation, reflection, and translation. Those are the main ones. And resizing, which is also called dilation, contraction, compression, enlargement, expansion, and another name for it is homothency, but you probably won't see that name soon. And the shape can become bigger or smaller in it. So a shape can become when one shape can become another using only rotations, reflections, and translations. It's called congruence. And two shapes are similar when you also need to dilate them, as in addition to rotations, reflections, and translations. Okay, now here's your next example. Okay, so let this distance be x. And then, so you know that n is a midpoint? So this to this is 1 to 2, so this is 2x. And also you know that this equals this because it's a square, so this is root 5x. And you also know that this is equal to this because the ratio of this, because the ratio of this side to this is 1 to 2. So the side length of this square is 2x, while the side length of the whole square is 2 root 5x. So the ratio of their areas is 2x squared over 2 root 5x squared, which is 4x squared over 20x squared, which is 1/5. Okay, so this is Shoelace formula. Mm, And by the Shoelace formula, find the area of a triangle with vertices of these. Okay, I'll just go over this fairly quickly because you likely won't need this for AMC8. So you just shove in the numbers 1 times 12 plus 4 times 16 plus 9 times 3 minus 3 times 4, 12 times 9, and 16 times 1. Yep. And then when you do the math, it goes to 33 over 2. And this is Pick's theorem, another thing you won't really need for AMC8. And this is just shows that if that's just a specific example. And now for this one, please do it. Okay, so the area of the shaded region. You can split it like this. So there's a total of 3 squares, and there's a total of 6 of these small triangles, and 2 of these small triangles have the same area as 1 square. So if 3 times plus 6 times 1/2, which is just 6. Okay, on to the final topic for today, which is 3D geometry. One common method of solving 3D geometry is by taking a plane that crosses the object and looking at the image on the plane. And another way is a net, that the 2D construction that can be folded up into a 3D shape. And now here are some common 3D polyhedrons, and this is these are what they look like, and these are some possible nets for them. Okay, and now here's a bigger list. Sphere, torus, it's very likely you won't need this. Cylinder, cuboid, box, rectangular prism, cube, cone, triangular pyramid, square pyramid, triangular prism. And now here's your first example. Okay, when the problem says area, it means surface area. Okay, so the surface area of this sphere is 4 pi times 6 squared, which is 144 pi. And when you increase the radius by a factor of 5, you increase the surface area by 25, which is 25 times 144 pi, which is 3600 pi. And now here's another example. Okay, so this is a cross section from the point of view of the plane that goes through here and here and center, like this. Okay, yeah, okay. And then so this distance is r root 3, and this is r. So then you get that 4 plus 2 root 3, r equals root 3, because a space diagonal of a cube is always s root 3, where s is a sine length, and you're given that it's a unit cube. So then you get that r equals square root of 3 divided by 4 plus 2 root 3, and you can clear out the denominator to eventually get 2 root 3 minus 3 over 2. And now for a sphere, the volume is given by 4/3 pi r cubed, and the surface area is 4 pi r squared. And for cylinders, the surface area is 2 pi r squared plus 2 pi r h, and the volume is 2 pi r squared h. And the lateral surface area would be 2 pi r h. A sphere doesn't have a lateral surface area. For a cone, the surface area is pi r s, where this length is s, and the volume is 1/3 pi r squared, and the lateral surface area is pi r s. For a rectangular prism, the surface area is this, and this is the volume, and these are the surface areas and volumes for triangular prisms. Okay, now here's your next example. Okay, so for this problem, v equals 4/3 pi r cubed, and you plug in r equals 3, so you get 36 pi. And the new volume v prime is 4/3 pi times 2r cubed, which is 8v, which is 288 pi. So a polyhedron is any 3D object with such that all of its faces are 2D polygons. And so in a polyhedron with V vertices, E edges, and F faces, this is always true. Okay, so a regular polyhedron is a polyhedron such that all of its faces are identical regular polygons, and there's only five of them. The platonic solids, the tetrahedron, the cube, the octahedron, dodecahedron, and icosahedron. So the tetrahedron is this. This is a cube. This is an octahedron. I believe this is an icosahedron. And the dodecahedron is triangular faces, is 20 triangular faces.
Wait, that's a dodecahedron on the pentagon face 20.
Okay, okay. I'm not fully sure. This is a dodecahedron, and the last one is has 20 triangular faces. And I won't bother drawing that out. You can find it on your own. Okay, so we're on the exercises, and we're probably only gonna get to this one tonight. Okay, so a hint for the problem is that the ratio of the area of triangle AXY the area of triangle ABC is AX over AB times AY over AC. AX over AB times AY over AC. Okay, so using the hint I gave earlier, this equals AX over AB times AY over AC, and this is pretty well known. You can use this, you can easily prove this, but not in a way, not in a very easy way, synthetically. So AX over AB equals 4 over 7, and AY over AC is 6 over 10. And when you multiply these, you get 24 over 70, and that simplifies to 12 over 35. And that's it for tonight's class. Thanks to my little brother Gordon for helping me be a teacher's assistant. And the video and handouts for this class will be posted either later today or by tomorrow. Bye.
Thank you. Bye.